So we're looking in this section at rates of change, and rates of change are where we're looking at a change in one quantity with respect to another. So a common kind of, I suppose, expression for that would be, let's say, a change in height with respect to a change in time. Now the way that we write that, we use the D to represent change, and we use variables to represent the different things we're looking at. So for example, here I might be looking at height and time. Okay, we also have to think about the units that we're using as well. So if we were looking at something like dh dt, change in height with respect to time, you might look at that in units of, say, height in meters over time in seconds. So that would look like meters per second. Okay, so that's the type of thing you're looking for. You're looking for the units in these questions. Then you're also thinking, well, what would the rate probably be that I'm looking at? And then going through and working to find the rate that you're actually interested in. So in this question here, you can see we've got a rectangular prism being filled at a rate of 0.00042 metres cubed per second. Find the rate, and you've got two rates here, at which the height is increasing. Now, what we need to do before we start a question, think about what we know. Okay, so looking at the question, I can see some units here, and I'm actually going to specify a few variables that I'm going to use. Now you can see you've got time here. I'm going to let time be t, and that's going to be in seconds because I can see I've been given a rate in seconds. I'm also going to look at volume, and I'll let the volume equal v, and you can see that the volume here is in meters cubed. And if you look at the picture, you've got different lengths here, and we've got this height. So I'm going to look at the height. I'm going to call the height h, and you can see that that's in meters. So I know some of the units already. Now, first thing I can do is look at this expression here. This is a rate, and you can see that it's meters cubed per second. Now, meters cubed per second is going to be a volume, so a change in volume with respect to a change in time, because this is a time unit, and the value of that is 0.00042 meters cubed per second. So that tells me what dV dt is going to be, the rate of change of the volume with respect to time. So I'll keep that one there because that's useful. Now we're being asked to find the rate at which the height is increasing. Now whenever it has a question asking you that, it doesn't have any other units, it would be with respect to time. So what we need is the change in height with respect to a change in time. That's what we need. Now we currently have a link between v and t. It looks like here we're going to need to incorporate h somehow, so it's a good idea to look back at your diagram or your situation and think, how can you link maybe the volume that you have and the height that's in this picture. And we know that volume for a space like this where the water is filled in would be length times width times height, and in this case our length is 3, our width is 2, and our height is h. So this is 6h. And remember that volume has to be in units, so it would be meters cubed. So we'd have 6h meters cubed for V. Okay. Now I can see that I need dH and dt for my expression. And the first thing I do is I look at what I have. I've got dV, that's not useful, but I do have dt, so that's cool. That's part of what I needed. I also need a dH, and I can see here I have a relationship between V, I'll just write it out again, and h, 6h. You don't have to put the units if you don't want, I just put them there to keep track of them. So I can see there's some link between v and h. Well, why don't I differentiate this with respect to h so I can introduce a dH? So what I'm going to do is differentiate both sides with respect to h, and differentiating the right side will just leave us with 6. Now in terms of the units, this is a volume, so meters cubed, per height, and the height is in meters. So what you'll see here is that the units actually cancel down, so you end up with meters squared. So dV dH is actually 6 meters squared. Okay, so what we've now got is we've got two, and I'll actually put a box around these two important quantities, two quantities that we can use to help us find what we need. Okay, so what we do is we actually use chain rule for these situations, and we look at what we have and what we need. Now I can see here that I need also dH on the top, and I have dH, but unfortunately it's on the bottom. So what I'm going to need to do is actually flip this over so that I get the dH on the top line where I want it, which means then flipping the 6 over as well. So I'm just going to write that underneath here. So that implies dH dV, just flip everything over, that becomes 1 over 6 instead of 6 over 1 meters squared. So now we can use the chain rule, and chain rule is just multiplying your differential quantities together. So we know that if we have dH dt, we can take dH dV and multiply it by dV dt. Why? Because if you look at this expression, the dV's will cancel and they'll leave you with dH on the top and dt underneath. So that means that all we have to do is actually just put in the quantities we know. So dH dV, well, that's 1/6, and that's meters. In fact, and what I should have done here to make that a bit clearer, oops, is that meters squared should be underneath as well. So all we have to do, put that in there, meters squared times dV dt. Now dV dt is 0.00042 meters cubed per second, and you can see you've got some cancelling here of the units. The meters cubed will cancel with the meters squared just to leave you meters, and then we have to take 0.00042 and divide by 6. So I'm just going to put that all onto this side here so we can see our answer. I'll just do this in a different colour, I'll do it in dark blue. So we've got dH dt equals 0.00042 divided by 6, and you can see the units here are meters per second. And if we actually put that into the calculator, you'll get 0.0000707 meters per second. And it's a good idea to check your units. Look at what you have on the top. Height, well, that should be meters, and time, well, that should be seconds. So you've got the right units there. So what that means is that the height of this particular fluid is increasing at a rate of 0.00007 meters per second.